We're going to start chapter 12. I have to warn you, chapter 12 has a lot of stuff in it. It's rotational motion and torque, but it also incorporates center of mass, moment of inertia, and static equilibrium, as well as angular momentum. So there's a lot of stuff in chapter 12. All right, quick reminder. So when we're talking about a rotating object, so let's talk about a spinning wheel. Okay, as the wheel spins, remember we measure its motion, and if I mark a point on the wheel's spinning around this point here, it moves at angle theta. Okay, well, that theta we measure in radians. The reason we do it in radians because that means it's a very easy conversion. If you want to know this arc length here, it's just going to be equal to S is equal to theta times R, as long as theta is in radians. Remember, we did this way back in chapter 4. I'm just reminding you of that. And the velocity at each point is equal to omega times R, where omega is how many radians per second it's rotating, or its angular speed. And remember, every point on here has the same omega on this spinning wheel, but the velocity is different because in the period, the time it takes to go around, the point out here has gone a lot further distance than a point in here. And so its actual velocity on the outside is much higher than it is in here. But it still took the same amount of time to do 2 pi radians, so omega hasn't changed. All right, and remember the period is equal to 2 pi r over v, that's a pi, or we can rewrite this as 2 pi over omega. All those are equivalent to each other. This should be review for you, and remember alpha is equal to A tangential times r, where alpha is the acceleration of the wheel. All right, so that's pretty much just a review of what we've done. I just want you to keep those things in mind. All right, now we're going to talk about something called the center of mass. The center of mass is if you take an object, an extended object. So we've always been talking about objects, but we've always treated them as a point. When we did our free body diagrams, we would always make it a single point, and we draw all the forces as acting on that one point. Well, we realize objects aren't single points. There's a point or a specific region in there which we call the center of mass. And if you take like a ruler, if the ruler is uniform density along it, the center of mass would be exactly at the center of the object. What that means is if I apply a force upward right here, exactly equal to gravity going downward, then I can balance that force or balance that ruler by holding it at that one point. So I can think of this in a different way. I can think, oh, so what I'm really saying is gravity's acting on all the matter on the whole thing. But I can sum up all the gravity's forces on every little piece of matter, and it acts like its gravitational pull is coming from a single point at the center of mass, also sometimes called the center of gravity of the object. So to hold that up or to counteract gravity, I only have to apply a force at that one point. Now if I apply a force out here, it's not going to work because if the force is going out here, gravity's pulling here, the whole thing's just going to spin. Okay? It's going to create a torque, which is what we're going to get to later. So what we really need to know is we have to understand what the center of mass means and how we calculate the center of mass, because that's where gravity acts on an object. Okay? And this is really important when if you're going to be an engineer and do any kind of mechanical engineering where you're saying, okay, I have an object, I want to know how it moves. You have to know the center of mass because everything acts about that center of mass or that center of point. So the way we calculate center of mass is, let's do it for a two-body system first. Think of it this way. Remember when you were a little kid and you had a seesaw or teeter-totter? And you put a really skinny kid on this side over here. Okay? But you had their bigger sister over here. If the bigger sister was out here, then they would pull down this side of the seesaw and this person would go up in the air and they couldn't get down at all. But if you move this person in, the person with more mass right here, okay, you got them closer to the center. There is a point where you could balance, where you could exactly balance each other. Okay? And from a physics point of view, I'm going to call this M1. I'm going to call this M2. And this is the fulcrum, or the rotation point right there. So the distance to that, we're going to call this R1. We're going to call this R2. And then from physics, M1, R1, the mass times the distance it is away from the rotation point, or the center of mass, has to be equal to M2, R2. So it's very easy. If you have more mass over here, you have to have a smaller radius. If you have less mass, you have to have a bigger radius. And that will balance out as long as you... So what you're trying to do is you're trying to get the center of mass to exactly match the rotation point. But most of the time we don't know where the center of mass is, so it's hard to measure R1 and R2 if you don't know where this position is. So usually we're measuring the position from somewhere outside. So let's say I have two masses here. We're just going to use balls now, M1 and M2. And I want to figure out where the center of mass is, and they're not the same mass. I want to know where the center of mass is. First of all, you always have to remember the center of mass is going to be closer to the large mass. All right? So we know it's going to be closer to M2 than it is to M1. But we don't know where it is in here. And I don't know where to start, so I can't measure R1 and R2 because they're supposed to be measured from the center of mass, but if I don't know where that is, I can't calculate that. But I can just make some arbitrary position out here. A reference point. And then I can call this distance to its center mass R2. I'm going to call this distance out here R1. And then somewhere in here is the center of mass. We're going to call this R center mass, COM. Okay? And that's what we're trying to figure out. Well, this is an easy problem. What it becomes is the mass total times R center of mass is just equal to M1 R1 plus M2 R2. Okay, so all I'm going to do is say that the total mass of the whole system, in this case it would just be M1 plus M2, times the center of mass has to equal the sum of each of these. And I can set this datum or this registration point anywhere I want. Now, remember this defaults to this. If I'm already at if my distance here is 0, so I'm at the center of mass, this side goes away, right? And then one of these, R2, would be negative, and so I flip it over here and that becomes that. So this equation would become this equation. So this is a special case of this. This is the more general case. In fact, we can make this even more general and say that the mass total times the R center mass is equal to the sum of all particles M sub I, R sub I. So if we have more than two particles, we can just sum up all these particles. Now that works great when you have indistinct particles, like all these little particles, but lots of times we don't have distinct particles. We have like a rectangle, a continuous object. Well, as long as the object is uniform density, the center mass is going to be at the center of the object. Now what gets trickier is if you have an object that's shaped like this. Then where's the center mass? Well, the center of mass is not going to actually be inside the object. And the easiest way to do that is you treat it like two objects. We say, okay, let's make this one rectangle. We're going to see that has to be the center of that rectangle, and this is another center of mass. Now we got two particles, we got two center masses, and we get our datum point, we mark it, we have to do it in 2 dimensions, so lots of times you have to do this both for x and for y, and that's how you figure out how to figure out where the center of mass is. So you take a geometric shape, you break it into regular solids that you know has a center, like rectangles. Okay? That's the easiest way. Or you can turn this into an integral if the mass is a function of its distance. So if you have a mass that varies with distance too, so it's non-uniform density, you can do that too, but then this becomes an integral of mdr, or actually, yeah, where m is a function of r. So that's the way you calculate the center of mass for an object. All right, remember in 2 dimensions, you have to do this twice. So you have to do m total times r center of mass in the x direction is equal to the sum of I equals 1 to n m sub I times r sub I sub x. And then you have exactly the same thing in the y direction. Sum I equals 1 to n m sub I r sub I sub y. And then you get a r center mass in the x, r center mass in the y, and then you have to combine those to figure out where the center of mass of the object is. That's how you do center of mass problems. So that's what problems 7, 8, and 29 are, and those are the ones that you should do first, are how you do calculate the center of mass of an object. All right, that's it for this video. There's going to be multiple parts of the chapter 12 because there's so much going on here, but the first part is just center of mass.